Welcome to Missing the Mark, where we look for meaning in strange places. I'm Christopher. Today I want to look at the assumption that physics explains everything. And I want to be clear, I'm not doing this because I'm saying it doesn't. I don't, in this sense, have a conclusion that I am driving towards. My point in this video is not going to be summing things up to, therefore this is the case, or therefore this is not the case. All I want to do is bring up the kind of interesting thing to think about what is assumption and what is it that we actually know. Now, there's a joke, which is that physics is applied math, and chemistry is applied physics, and biology is applied chemistry. Did I say chemistry the second time? Chemistry is applied physics, biology is applied chemistry, and sometimes you get to other subjects like social studies is applied biology, something like that. There are variations on this joke. And it's that one that chemistry is applied physics that I want to look at. And it's not strictly chemistry in the sense of like the actual study of chemistry or chemistry class. It's that everything bigger than subatomic particles is all just applied physics. And in particular is explained by the laws of physics that we know. Now, the reason I want to look at this, as I said, is not to drive any point home, nor is it to claim that physics is false. We don't know whether physics is true or not. That's intrinsically the nature of a hypothesis and evidence that fails to disconfirm it. The whole nature of the enterprise of science as we do it in the modern world can never truly come to the conclusion that it's accurate, only that to the best of our knowledge it is not inaccurate. That said, like everyone else, I tend to strongly suspect that it's at least largely true. So, why am I doing this? Just because it's really, really interesting to be realistic about what is knowledge and what isn't. And this is not just the, it hasn't been disconfirmed thing. I want to look rather at the limitations of what's actually going on. Now, to give an example of one of these limitations, there's an interesting question to be asked about radio frequencies. And I asked this actually of a radio engineer, and so the answer was kind of interesting. The question is, when you talk about a radio frequency, like let's say you're transmitting off an antenna at 100 hertz, is this actually 100 hertz electromagnetic radiation in the same way that, because all electromagnetic radiation has a frequency, and I can't remember. The nanometers is easier for some reason, to remember than the actual frequency. I think it's in visible light's in the terahertz or something like that. Anyway, it's it's higher than that, petahertz, higher even than that, I think. Visible light's roughly in the very, very loosely 700 to 400 nanometer range, which, given that light travels at 300 million meters per second, translates to, I don't know, something in the petahertz, I think. Maybe the terahertz. Anyway, but so that's the frequency of the vibrations of the actual electromagnetic radiation. But when you transmit off an antenna at 100 hertz, are you transmitting 100 hertz electromagnetic radiation, or are you transmitting a higher frequency radio signal at 100 times per second? In the same way that, like, if I took a flashlight and turned it on and off 100 times a second, that would be a 100 hertz signal, but the underlying electromagnetic radiation would be much, much, much higher frequency. You can encode a lower frequency signal on a higher frequency. You can't do the reverse. But anyway, so which is it? And the answer is no one knows. 100 hertz off of radio frequencies in general are defined to just be when you pulse electricity in this many times per second, what comes out. We don't actually know what the actual frequency of the electromagnetic radiation is because the energy levels are so much lower than in visible light that nobody can devise an experiment whereby you can actually receive a single photon. They are so low energy, you can't do it. You can't even come vaguely close to doing it. You can't do anything that comes close to approximating coming close to doing it. You just can't. You can only detect these things when there are untold numbers of them, and then in aggregate the energy gets high enough for human beings to detect. Therefore, we have no way of telling the difference between these two things, and we get just a functional definition of radio frequency, that it's the frequency of electrical signal, it's whatever comes out when you pulse the electricity in and out of the antenna that often. And I think it's that, or it could equivalently be defined as like when you expose that to an antenna, the electricity that comes out, what is its frequency? So, this brings us to the very interesting thing that when it comes to phenomena in physics, for the most part, the things are so small and the energy levels so low, we can't actually interact with them. We can't perform experiments on individual subatomic particles, or small atomic subatomic particles. We can't measure these things individually. We cannot interact with them at the sort of energy states they normally are doing in the real world, or in the ordinary world. So if you look up, we always are doing these things in aggregates and in strange circumstances. But if you look up, for example, things like super colliders. Well, what are you doing in super colliders? Well, you're super colliding. You are doing incredibly high energy physics. You are throwing particles at such large numbers of them too, at such astonishing speeds that when they slam into each other, it's actually possible for extremely sensitive instruments that human beings make to detect this stuff. Well, there's kind of an interesting thing about the fact that we can only interact with these things at incredibly high energy states. And to give an example of the phenomenon that I mean, consider what it's like to interact with a human being at a very high energy state. Human beings at low energy states do all sorts of very interesting things. They talk to you, they play games, they read books, they take naps, they think thoughts. What does a human being at a high energy state do? Well, they just go on a ballistic trajectory. If you fire somebody at a wall at 80,000 miles per hour, you pretty much can tell where they're going to hit. And you're not going to have any sort of interesting conversation with them. They're not going to just on the spur of the moment decide to take a walk down to the corner bake shop and buy a croissant. They're just going in a ballistic trajectory until they hit that wall and then go splat. Humans at high energy don't exhibit any of those interesting behaviors that they exhibit at low energy. And also, in truly astonishing numbers, if you look at tens of thousands of human beings, like look at human beings in a baseball game, from get a drone, fly it to a few thousand feet up, look down where each person's maybe a pixel, if that, and observe them, and they'll look a little bit like water. As they flow, at some point they'll flow out, and you'll see them merging from like all the seats into the little rivulets, and those things merge into bigger stuff, and they tend to observe basic hydrodynamics that that if you get a constriction point, then flow slows down, and then when you have like a long tube, you tend to get relatively straight laminar flow, etc. Turbulence slows it down, increases pressure on the sides, yada yada, lots of things. Point being, when you look at human beings in tremendous aggregate, all the interesting things they do basically go away. When you look at human beings in extremely high energy circumstances, all the interesting things they do tend to go away. Now, what are the things we actually, for the most part, though with exceptions, care about when it comes to, say, things like electrons? Is it what they do when they are being fired at 1/10 the speed of light against other electrons in a super collider? Well, if you're a physicist, yes. Otherwise, no. You find interesting, to the degree that you would even find any of this interesting, what they do, for example, as you're baking bread, what they do when they are part of the molecules that make up the neurons in a human mind. All of these things are, one, not stuff where you can observe them just in general aggregate. You can, like an EEG, electroencephalogram, the thing where you put all the electrodes on someone's skull and sort of measure electrical activation. Or the alternative one, the functional MRI, where you use magnetic resonance imaging to do things like you're watching it in real time. to figure out things like where's blood flow, where's there more blood going. And you could say, aha, when a person's thinking about trout, this area of the brain gets more blood, therefore this is the trout portion of the brain. Yeah, and in some sense this isn't completely false. I mean, the results in fMRIs, etc., typically, when you look into them, massively overstated, but in any event, not really the point here. The point is that when you look at things in this aggregate, yeah, I mean, there's stuff you could say about them in aggregate, but you're missing out on most of what's actually going on. Now, maybe it's all actually incredibly simple, and it's, just this very, very simple little thing, and you don't really miss out. Maybe it's all described by, the physics that we happen to know. Maybe. Or maybe there's actually a whole bunch of other interesting physics when you're at low energy states, and we can't tell any of it because we can't observe really, really small things, and we can't observe stuff at very low energies because we're just too big, and in order to interact with it at all, our energy states are just so massive that you can't do it. To give sort of an analogy, imagine there was some sort of alien that was so big that the Earth was a speck of dust to it. In order to get enough light to actually see anything, it would have to shine a light so bright that it would cause forest fires, it would cause steel to melt, it would cause the thing to burn on the small scale, on the really, really small scale. And so, such a giant alien trying to look at this tiny little thing when he shines his flashlight in order to try to make out some of the detail in there to get enough light bouncing back to hit his eye, which is, 100,000 miles wide. Well, he would find that whenever he looks at these tiny little rocks, they don't have anything interesting on them. Every time you shine a flashlight on them, in order to actually see it, all you notice is that, like, they're maybe a little bit of smoldering, something like that, often kind of black and charred. Not much to see there. Also quite possible. Now, as I said, I'm not here trying to argue to any conclusion about physics or really about anything else. All I'm trying to suggest is, if you think about it, you will know that there are some significant limitations to our knowledge. And moreover, this is not the sort of thing where we looked and didn't find anything. This is the sort of thing where you can't look. You can't look because the stuff is too small for you to see it. And you can't look because by the time you are shining enough energy on the thing in order to be able to get something back that you can actually perceive, the amount of energy that you're going in will overwhelm the amount of energy that was originally there, and so you cannot actually perceive the thing undisturbed. Yes, we have small microscopes, but they all shine lights, and those lights are very bright in comparison to the really truly tiny stuff that you might want to look at. And so this is not a case, as I said, of we looked and there was nothing there. This is a case of we can't look, so we have no idea whether or not anything is there. And it's just kind of interesting to think about that we have no way of knowing whether or not there is stuff that is there or not, because we can't look. There is clearly some stuff we can tell is there, because when you look, you actually find it. And then there's the stuff you just can't look at. And you can do with that whatever you want. Until next time, may you hit everything you aim at.